Okay, hello everyone. I'm Marcin. I work at Qilimanjaro in the theory team. And I will talk about something different from the main scope of this conference. However, I think this is quite interesting from the global perspective on the quantum technologies we are facing. And first of all, thanks for the organizers to put this conference all together. And so this work appeared recently on the archive, and this collaboration between Tana Usu and Kuba Zakrzewski from Jagiellonian University. Better? Okay, good. And Piotr Sieland, who works at the Barcelona Supercomputing Center here. Okay, and the field we will be covering here is intersection of the analog quantum simulators, quantum correlations, quantum metrology, and the complexity theory. And basically, we'll be talking about the question, when really quantum state is hard to simulate it classically and where it is not. And we'll put this in the context on the quantum metrological resources. So a little bit of the context. We are living, this is like the narrative that in the second quantum revolution. What does it mean? It means that we technologically would like to utilize controlled, generated, stored quantum correlations in many-body quantum systems. And there are four pillars of this quantum teleological, let's say, breakthroughs. There's the quantum simulation. So basically, we cannot solve many-body problem analytically. We are facing classical simulations. So we go to the lab, we talk to experimentalists, we say, we have this problem, this Hamiltonian, this description, please go to the lab, construct this dynamics, let's make the measurement, and let's extract observables, and we'll learn some new physics. We have quantum computing, so basically all paradigm of quantum computations, which basically you are all working here with this topic. But we have also quantum metrology, so basically with the quantumness, with the quantum correlations, we can beat short noise limits. We can go to the Heisenberg scaling, so we can decrease the precision, increase precision, decrease the variance of the measured quantity. And we have also quantum communication, so all safe protocols for sharing key distribution, which helps us to send information with a safe way, okay? And all those methods are utilizing many-body quantum states and the quantum correlations. And the whole Hilbert space, basically of many qubits, many-body system, can be somehow presented as the hierarchy of quantum correlation. So here we have no-entangled states, like basically separable states, and we can distinguish bipartite states, and we increase the complexity of the structure of the quantum correlations, okay? And there is no doubt that those quantum correlations are useful for 3 out of 4 tasks. Simulation, metrology, and sensing, and communication, no doubt, quantum correlation helps. However, there is no quantum advantage yet. There's no proven that we can, with the quantum computing, we can do something better, which we cannot do with the classical methods nowadays. Like, this is the current status of people working in the quantum algorithms. It's not my opinion, it's something I repeat after people much smarter than me. And we can make some observations. For example, we know that having a lot of entanglement is not equivalent to have problem which is hard to classical simulable. And the best case are the GAZ state. We'll talk about that. They are like super entangled, but they are quite easy simulable with the Gottesman-Nil formalism. We'll talk about this later. On the other hand, we have tensor networks, powerful tools, which allows us to study many plethora of quantum states with area law scaling of the entanglement. However, they are hard. They have hard time to simulate GAZ states or cluster states. So these are like the examples which justify why we need some measure which tell us when quantum state is hard to simulable on the classical machine. So we need some dictionary for that. It will be quite short. So we'll try to answer the question. Gottesman and Nil answered that question in the 90s, but for us, we ask the question, where quantum state is hard to classically simulable, and what does it mean, basically, simulation? So we need to define a few things. So the Pauli string is basically product of X and Z operators. We have all possible combinations for the n-qubit systems. And the Clifford unitary is the unitary matrix which maps Pauli string to Pauli string. So when we act with the Clifford unitary on some Pauli string, we got another representation of the Pauli string. For example, we do not have the superposition of two Pauli strings, okay? And those two definitions allow us to define the stabilizer state. So stabilizer state is the quantum state which is constructed through the acting of the Clifford unitary on product state in the computational basis of n qubits, okay? And to give some examples, what are the Clifford unitaries or how we can construct them? Clifford unitaries for the n-qubit systems are constructed from the Clifford gates, and this is the Hadamard gate, S gate, and C node, okay? And Godesman-Neal theorem says the following. If our input state is basically the stabilizer state, so we have Clifford unitary acting on the product state, and our circuit contains like many of Clifford unitaries, and we have measurements in the Pauli basis. It means that probability, so probing from this probability or simulating this probability can be done in polynomial time algorithm. So basically, it means that we can simulate outcome of this probability easily in the classical machine. Other examples, for example, boson sampling. This is proven that this is hard to simulate classically. If we repeat the experiments in the boson sampling machines, we cannot simulate the outcome effectively with the classical machines. And this is the example of the opposite. We can do it very effectively classically. And with this formalis, Pauli strings, we can simulate up to 1,000 qubits. So this is like also quite important thing, that this formalis allows us to simulate much higher than we have machines today, okay? So there's the question where the quantum state is hard to simulate. Sorry, where the quantum state is hard to simulate. So basically, we need to go above or outside the Clifford circuits. So we need to add some non-Clifford gate, and this is T gate. It's called non-Clifford gate, and the Clifford gate plus T, they form universal set of quantum gates. With this, we can simulate any quantum state in the Hilbert space of qubits. Okay, and recently in the literature, they appear that terms like which magic resource or non-stabilizerness. So it says how many non-Clifford gates do we need to create a given quantum state. So this is conceptually easy because we say this state is simple to classical on the computer because it has small number of T gates. Another state is hard because it has many T gates. But this conceptually easy definition, however, very hard operational. We don't know how to calculate this quantity. I mean, it is hard. So in 2022, there was a new paper which introduced the measure, operational measure, allowing us to quantify this non-stabilizerness. And it looks like ugly, but basically, this is the question. We have quantum state psi, pure state, and we calculate overlap with all possible Pauli strings. We sum up all those numbers, and we get something which is called stabilizer Rényi entropy. And what are the properties of this measure? First of all, this is invariant under acting of the Clifford unitary, so this is good. If we act with the Clifford unitary, it doesn't change the magic. It is additive under the tensor product, and it is strictly zero if we have the stabilizer state. And it is bounded from above by number of qubits, and this is maximally non-stabilizer states. So this measure gives what is the maximal value of this non-stabilizerness. Okay, so we can divide the Hilbert space into low magic state, large magic state, or stabilizer states. Some examples as the still background information. For example, we can talk about family of states known as the cluster states. Those are states represented as the graphs. Each node of the graph corresponds to plus state, and edge corresponds to the control Z gate. And for example, you can convince yourself that the star graph is the G8Z state, so maximally entangled state. However, it's super easy to simulate on the classical machine. Two-rank graph, this is state good for the quantum metrology as well as the G8Z state. And we have also cluster states. So there are basically grid of qubits with these control Z interactions. And these states are the resource for other paradigm of quantum computing, which is called measurement-based quantum computing. We introduce the quantum entangled state, and we prepare measurements, and we perform quantum algorithm. But this work asks the following question. What do we know, what can we say about magic or hard simulability in the analog quantum simulators? And we'll focus about quantum simulators for the quantum metrology. And we'll talk about one-axis twisting protocol. So basically, one-axis twisting protocol is the Hamiltonian with all-to-all sigma Z couplings, so this collective SZ square. And why this is important? Because this state generates, this protocol generates states which are useful for quantum metrology. In particular, it generates spin squeeze states, so making measurement in that direction minimize the variance of the observable. And it also generates G8Z states at the end of the protocol. Spin squeeze states, as the quick recap about metrology, can be characterized by the Fisher information and spin squeezing parameter. And basically, spin squeezing parameter, the lower the better. If we have spin squeezing parameter smaller than 1, we have some quantum enhanced advantage in the metrology. And there's also other things related to those states. Those states, they have different robustness to the external noise. Spin squeeze states are very robust to they are robust to noise. And the G8Z, which gives Heisenberg scaling, is super vulnerable to any perturbation. And the question we ask, can we characterize metrological usefulness, many-body correlations, and usefulness for the robustness against perturbation with the magic? Last thing, important for the context, is that one-axis twisting protocol generates arbitrary depth many-body correlations in the system. It can be characterized by Q correlator. Without going to the details, with the Q is equal n-2, we know that this is G8Z state. And knowing value of the Q, we can certify entanglement depth of non-case separability. Without going to the details, we have to know if Q is larger than 0, state is quantum Bell correlated. Okay? And the one-axis twisting protocol has been known for the 40 years already, and there was always a lot of effort to construct or engineer this in the lab. And one of the approaches is to use, I came from the AMO physics community, so optical lattices, bosons, or fermions. So we have shown that, for example, Bose-Hubbard model with two-component bosons generates effectively one-axis twisting dynamics. Similar thing takes place for the Fermi-Hubbard model with external lasers, introducing this kind of couplings. And this also generates one-axis twisting states. So the questions. How magic scales with the system size? Because we know the largest value is n, so this is linear with the system size for the hardest state to simulate. How magic is related to the Bell correlations? Because we know that for the G8Z state, this is 0. What are the relations for the lower correlated states? And is there any link between magic and robustness to noise? And now I'll talk shortly about the results. So calculating from the definition is very hard because it requires projections of 4 to the n Pauli strings. So this is super hard. For permutational invariant state, there was recent paper by Passarelli. They show that you can utilize this symmetric subspace and you can use n to the n cube number of measurements. It's better, it's not exponential, but it's still quite high. For 100 particles, we need 10,000 measurements. It's not so good. And in our work, we showed that basically you can extract the non-stabilizerness entropy for the large n limit, knowing only 6 measurements. And so basically, this is a very experimentally friendly result. So let's talk about evolution of the M2 in the one-axis twisting protocol with the relation to the correlations. Basically, we have three types of states. We have spin squeeze states here. We have states which are coherent superposition of many heads, like Kitten states. And here we have G8Z state. And we know that G8Z state has 0 SRE, because this is stabilizer states. And we see that the Kitten states, superposition of the many heads, they have finite SRE. And now is the question how it scales with the system size and with the Bell correlations. And now we are going to like the very final results. Basically, we show that the SRE, so magic, for best squeeze state with the minimum value of the squeezing parameters of the best metrologically useful states, it scales logarithmically with the number of particles, and it correlates with the depth of Bell correlations. So basically, we see that there's, okay, more correlation, more magic. However, when you talk about Kitten states, the SRE is basically constant with the number of particles. So we see that it is not harder with the larger of particles to simulate those states. And the Bell correlations anti-correlate with the magic. So it means that magic should be treated as the independent resource from the entanglement or coherence in the whole quantum business and quantum technologies. We also compared we calculate the results for the two-axis counter twisting. This is another method for creating metrologically useful states, and the conclusions are the same. Magic for the best squeeze states grows logarithmically with the system size. So basically, I'm going to observation and conclusions. Maximally, SRE scales logarithmically with the system size. It means that those states are easily simulable on the classical machines. We do not have quantum computers to simulate physics of those states in the symmetric subspace, which is not surprising, because this is still linear size of the Hilbert space. But we see something more interesting. We see some relation between robustness to noise and magic. So it means that states which are good for the metrology, which are robust to noise, they have non-zero scalable magic. And this gives some answer maybe why G8Z state is so bad for the metrology. In our interpretation, it means because it has zero magic. So magic is the resource for the quantum technologies nowadays, and we should focus on generating and utilizing states with high magic. And with that, thank you for your attention.
Okay, thanks a lot, Marcin. Questions? Yeah, there is one here.
Okay, thank you very much for your talk. So I'm curious. So, of course, magic is important for quantum computing, but it also is entanglement. Otherwise, we can also simulate things efficiently. Is there a measure of that combines both magic and entanglement? And another related question is, do you know how entanglement grows in those systems? Because you said that magic grows logarithmically with n. Is also entanglement growing at the same rate or so? Do you know?
So that's the point, that this is disentanglement in the classical sense, like the feature extraction. If magic grows, it doesn't mean that entanglement will grow. Mm-hmm. So it's hard to say. And this is basically one of our results, that for maximally Swiss squared, Bell correlations grows like sublinearly with the system size, mm-hmm. while magic grows way slower. On the other hand, we have these results that magic is constant. So n is the number of heads, but basically it is constant with the system size. And Bell correlation grows with the particle number. So this is something super curious to me. And this also opens other question. Why should we bother about measurement-based quantum computing? Because those states are classically simulable. So why do we even talk about this paradigm? Because there will be no quantum advantage in this magic perspective.
Okay. Thank you.
Thanks for the talk. I had a question regarding your approximation, which you reduce the complexity of calculating the magic. So is this like a one-to-one, or did you make are you getting approximate values of magic? I mean, what is exactly going on that you could reduce it so much, reduce the actual complexity of calculating this?
So first of all, we utilize symmetric subspace, okay? And this expression was basically done not from the very first assumptions, but on the other hand, it was analyzing Pauli spectra, and we observed that to arbitrarily low precision with the increasing numbers of the qubits, this formula works perfectly fine. I think this answers your question. So this is not approach, but rather trying what has done in the numerics and extract the most important contributions to the magic.
So there might be a chance that there's some state which has a large error compared to the exact calculation. That there is a chance. Would you say so?
Well, of course, but according to our checks, no. This fully exploits symmetric subspace and fully agrees, for example, with Pastorelli's results for the LGM-based models.
Okay. Can I ask one more? Yeah, just one small other question. So I'm curious that you showed that some magic states have large magic but low entanglement, right?
Yes.
To answer to this question just before, right?
Yes.
The scalability. So in my head, that would mean I could simulate it via tensor networks well, right? But then large magic means you cannot simulate it classically. So what am I missing here?
And another very valid point. With tensor networks, for example, you cannot simulate effectively GAZ state.
Yeah.
With all-to-all connections, exponential growth of the bond dimension. But this state has zero magic. So that's the point. That is a very fresh field, and we are walking through the fog, talking like this state is good or this state is hard for the classical simulations. So there are very cancelling statements.
Yeah. Okay. Thank you.
Okay. I have my own question. You show some geometry based a consideration of these states at the beginning, the graphs for that one.
This one?
No, the next one. This one. Yeah. So can you tell from the topology of a given connectivity if this is likely to generate high values of magic?
No. By definition, those states are zero magic. All cluster states, they're only constructed with the Clifford gates.
No, but I mean, if you have an arbitrary interaction, for instance. So
so if there is no control Z, but for example some parameters, or basically no, you have to calculate. No, you cannot.
Okay.
You cannot. You have to calculate magic and see how it scales.
Okay, thank you. So let's thank again Marcin.